In part 2 of the lab, you will use the process model parameters from part 1 to determine appropriate values for controller gain and the time constant for each of the 3 process controllers. When you first open the web page, automatic control will be disabled for the 3 controllers, as you can see from the grayed out input boxes. In order to enable automatic control, you'll need to enter a control law where it says, "Enter your code here." The command you enter in this box will be a single line of code using the variables specified above the code entry area. Let's examine what's going on here. This code block contains a function called controller, which runs once per execution cycle of the control code. In this lab, that means that this function is executed once every simulated second, as the time differential per data point is 1 second. You can think of this as if the controllers receive a new process variable once per second, and this code decides how to adjust the manipulated variable accordingly. Let's go through each variable that you can use in the code area one by one. The first variable, DERR, represents the error for a single discrete time step. This is defined as the difference between the set point and the actual process value. For example, if the temperature set point is 465 Kelvin, like it is here, but the column temperature is only 455 Kelvin, DERR would be equal to 10, because 465 minus 455 is 10. Next, we have the sum of the errors, designated by a variable called ERRS. And each time this function is called, the error from that time step is added to ERRS, the sum of the errors. This term will increase over time if the process variable is below the set point, or decrease over time if the process variable is above the set point. Our next variable is DMV, or the change to the manipulated variable. As you can see in the pseudocode, you will define the value of DMV. The text that you enter here will include the other variables listed, as well as mathematical operators such as plus, minus, divided by, which is a /, and the multiplication operator, which is an asterisk. You may also use parentheses and numbers here. So if I enter DERR plus 5 over tau I minus 2 times 3, that would be a valid control law, even though it doesn't really make much sense to use that in this particular context. So moving on to the next terms, KC is the variable for controller gain, and tau I is the variable for the controller time constant. These correspond to the input boxes under each controller labeled KC and tau I. So even though the code is the same for all 3 controllers, the values for KC and tau I will depend on what number you put in the input boxes here. Okay, let's implement a simple proportional only control law. In the input box, I will put DMV equals KC times DERR. And this is case sensitive, so be sure you don't accidentally capitalize or lowercase a letter that shouldn't be capitalized or lowercase. What this pseudocode says is that the manipulated variable, such as heat duty, bottom's volumetric flow rate, or valve lift, is proportional to the controller gain times the error. We can see that the auto mode toggle has been enabled for the 3 controllers, and we now have the option to enable automatic control on any of the 3 controllers. Once you press auto, that controller will operate according to a proportional only control law. Let's test out one of the controllers. I'll first enable auto mode, and then set the level controller's gain to -1, and the liquid level set point to 25%. After pressing Update and waiting a moment, we can see that the bottom's volumetric flow rate adjusts itself automatically to bring the liquid level to 25% full. I'll leave it up to you to determine what a proportional integral control law would look like, as you may find that proportional only control does not always yield optimal results. This simulation currently does not support derivative control laws, so keep that in mind. You'll be unable to implement PID control, just PI control. Also, this dashed line here represents the set point value, which in manual mode is equal to the manipulated variable. So when you switch between auto mode and manual mode, you may see spikes as it will be drawn with respect to the other y-axis. And now I've tuned the controllers to demonstrate how a properly tuned system should behave. I've blacked out the tuning parameters and the control law, as you should determine these parameters yourself via some methods such as direct synthesis, internal model control, or online tuning, among the many other possible methods. The process is currently at steady state, so let's perform a 20% step change to all three of the inlet conditions and see what happens. As you can see, the controllers are able to maintain the set point values, and the system can be considered stable even when deviations are introduced to the inlet. After getting to this point, all that's left for you to do is analyze your results. Like the first part of the experiment, you may download the simulation data by pressing Snapshot CSV and use that spreadsheet to do an in-depth analysis of your control schema.